Hello, welcome to Anson Griffin's occasional series in MATLAB tutorials. Today I basing them on second order differential equations, and none of this is my work, just to give credit where credit's due. So this is Harari and Childs from Texas A&M, and they have a number of second order differential equations and the MATLAB solutions. There are some of them there, and they're basically go from fairly simple to fairly difficult. So we're just going to look at one or two of them as we go along. So the first one up is a spring mass damper system, and as before, we have to replace this into two first order. We have don't know if you can see it now on the screen, because I just might zoom in a second. The mx double dot, the double dot refers to the second derivative, so it's a second order, and the single dot here refers to a single dot. So we have to break it up into two singles, and then here are some of the constants here. So we're looking at a spring mass damper system on forced response. We're given the values here, and if I just slide over a little bit, he works through the solution, and I just zoom in here again a little bit, so because I know before it can be hard to see. So that V equals x dot, and then rearranging we get that mv dot C plus kx equals 0. Now I think last week I may use y, and this use I may use x, but it's the same thing. You have to replace the second order 8 by 2 first orders. I think that was covered fairly well. So we rearrange this equation here, and v dot, hopefully you can see that, where v dot is the equivalent of the second derivative. We get change this over to the right hand side, and we get that. And then we get equations 4 and 5, and then we have the constants here. C over m is 2 epsilon omega n, and omega squared n is k over n. So the code is here, right? I'm just giving credit, it's there. And there's the MATLAB code. Now you might be critical here and say that the code is uncommented, but that's not really the point here. We're just trying to give you some idea of the MATLAB code. So I have a number of these made out here, if I can just find them. So there we are. So we're calling ODE45 unforced 1 t-span and y0, and our t-span is 0 and 4, and our y0 is 0.220. So just look at there we are, and there's E, M, K, omega squared, etc. We run it here, and whatever about the code not being commented, at least the figure is pretty decent here. Displacement versus time. Okay, and we can see it. It just starts oscillating, and then the damping effect comes in and just goes down to 0. Okay, I think we can shut that one, and we can shut that one. Now, next one up, you might download that yourselves if you're interested, because it's fairly well written. There's the graph we just saw. In the next few pages he just changes the numbers just and gets you to do a little bit of homework. The pendulum problem we did last week, So I can skip that one. Now, Coulomb friction. Just zoom in a bit, because I know my screen ain't the best. Left hand side, second derivative, just where the mouse is now, that dot, single derivative. Right hand side equals a load of mess. And there are some of the constants. As before, we substitute, we want to break down the second order into two first orders. He works through it here, and then he reduces this guy to this and this. And okay, and if you're doing second order differential equations, you should be able to figure this out, how to rearrange. MATLAB code, there it is, and then again you might say there should be more comments in here, but that's okay. Let's just have a little look. That's the function. Let's run it. And there's t versus time. Okay. I think that's alright. Might just look at the code for 1 sec. T span 0 to 2. Y 0. Okay. I think last week I had it as 2 columns. This time I have, or he has it as 2 rows. So that's row 1, and that's row 2. And how do we know we're on a new row? Because of the semicolon. There's the Coulomb friction. Okay, and there's my output there. Excuse me for yawning. Shut that down. The next one he did was airdrag. Let's down a little bit here. Oh, sorry, I've gone by it. So trajectory motion with airdrag, and I did a couple of plots like himself. He did the coefficients here of drag as 0.1, 0.3 and 0.5. Now obviously as the coefficient gets higher, you're going to go, or the projectile is going to go less and less and less. Just zoom in here again so that guys can see it. Double dot is d2x dt squared, single x dt dx, y double dot d2y dt squared, y dot dt dy. He rearranges, and then when he rearranges the two equations above, he gets that. Just pause there. Hopefully you can do that. You can see how they're getting slightly harder and harder. There's the function. Now the first time, the only criticism here, he has the coefficient of drag hardwired in as 0.2. So when he did 0.1, 0.2, 0.3, 0.4, whatever it was, you had to go in manually into the function and change it. There's the code. Now, I have my code out here. So, in this one here, the airdrag is 0.3. Come on. Sorry, the machine is having a rest. Can't click on that. There we are. So we run it this time, and the important thing here is hold on. And the other important line is axis. So I'm forcing x min to be 0, x max to be 0, sorry, x min to be 0, x max to be 100, y min to be 0, and y max to be 5. And hold on keeps everything the same way, keeps that figure up. So we run this, and there's my first car, and that's the coefficient of 0.3. Let's make that 0.2 now. Save it, Control S, run it again, and because hold on is here, it'll keep the figure. So that's so you can see now we've got the same plot, sorry, two plots on the same figure, I should say. We had 0.3, we had 0.2, now we have 0.1. Save that, Control S, go to here again, run it. So 0.3, 0.2 and 0.1. Well, by rights I should have put in a legend, but I think we're happy enough just to see those values. Okay, that's 3 of them. And again, if you're doing this yourself, just go back up to the very top. Solving problems in dynamics and vibrations using MATLAB. I don't have the web link to hand, but if you googled Childs and Harihara, you'd be able to find it. Okay, so thanks very much for listening.